Okay, here's another type of problem. The radius of a cylinder is increasing while the height stays a constant 6 centimeters. At a certain instant, the rate of increase of the volume of the cylinder is numerically equal. That just means the numbers are the same, even if the units aren't the same, to twice the rate of increase of the surface area What is the radius of the cylinder at that instant? Okay, let's find some rates. So at a certain instant, the rate of increase of the volume, so this is dV dt, numerically equal to twice the rate of increase of the surface area. So let's use A again, dA dt. What is the radius? Okay, so let's draw a little picture. We've got a cylinder. It has R. We know the radius of the cylinder is increasing, so that should be a variable. The height is a constant 6 centimeters, so that's just 6. So now we need a couple of equations. We've got area and volume. We don't have an equation directly relating the two of them, but let's write them both out in terms of the radius, because the radius is also in the problem, and let's see what happens. So we know that the volume of a cylinder is the area of the base times height. So the area of the base is pi r squared times the height, which is 6. Okay. And then the surface area, that's going to be 2 area of the base. Basically, there's one circle on top, there's one circle down here on the bottom. So if we find the area of each of these circles, there are 2 of them, that'll give us part of the surface area. And then we also have basically this tube that's forming the height. So we imagine that as if we had a little cylinder or whatever, something like this. And this top width, this distance, notice, is the circumference of that top circle. And this height is the same as the height here. So the circumference of the circle times height. So this is 2. The area of the base is pi r squared. Circumference is 2 pi r. And height is 6. So let's take our derivatives and see what happens. The 6 and the pi are just along for the ride. Two and the pi are along for the ride. Twelve pi is along for the ride. C dt is 12 pi r. Two equations, which is a little too much. So let's come back and look at what we're solving for. So we actually want to find the radius, so somehow we've got to get down to one equation with just an r in it. And we know that the dv dt is twice dA dt. So dv dt equals 2 dA dt. So we can at least take that out and sort of plug it in here. 2 dA dt equals 12 pi r. Times dr dt. Let's see where that gets us. Well, notice that we've got a dA dt over here and a dA dt over here. So that means that we can substitute all of this right into here if we like. That gets rid of another variable. So we've got 2 times 4 pi r dr dt plus 12 pi dr dt r dt. Okay, so now we're down to just dr dt and an r, which is getting better. Let's distribute this 2, just to make life simpler. 8 pi r dr dt plus 24 pi dr dt equals 12 pi r dr dt. Now, one of the things that I noticed looking at this is that every single term has a pi and a dr dt. So that means we can divide everything by pi dr dt. Oops. Presuming dr dt is not 0, which if the volume and surface area are changing, it can't be. So now we've got 8r plus 24 equals 12r, which makes life significantly simpler. Subtract 8r from both sides. Divide by 4. And the units are in centimeters.